Good. So can everybody online? Okay. So I'm going to start with the gyrimonad, which is related to the category of Markov kernels. Okay. So the gyrimonad, it's on this category MBLE, which is measurable spaces. And it assigns to a measurable space the space of probability measures on it. Then the morphisms in measurable spaces are the deterministic maps, and then the Kleisli morphisms are the probabilistic maps. So you have these two different categories, one of the deterministic maps and one of the probabilistic ones. Also, the other thing we can do is we can take two measures and form the independent product of them. If you have a product space, you can take a measure on each factor and produce the product measure on the whole thing. And the categorical structure there is that you get a lax monoidal monad and therefore a commutative monad. And that's the version of commutative monad I use, not the double strength, or the one where you start with a double strength rather than have a strength on one side and so on. So that's sort of in Fritz's original paper on Markov categories, that's sort of a motivating example. And also, I think Tobias kind of came up with Markov categories as this clever way of not having to prove you really have a monad. So before, when I'd be thinking of categorical probability, it's always like you have a probability monad and all this other stuff. But then what I've been doing is taking doing, instead of for measurable spaces, do it for measure spaces so that you can quotient out by null sets. And a lot of things in measure theory are only defined up to a null set, or almost everywhere, or one of these equivalent terms. So it's nice to get rid of them. And it would also be nice to still have a monad and still have the independent product of measures and so on. That's what this is about. Right. So what kind of measure spaces, or maybe you've never seen measure spaces. What is a measure space? So in this case, we really just have a set, which is this X, and a sigma algebra, and a measure. And then the measure is allowed to take the value infinity. It's not required to be a probability measure. And then the null sets are the sets of measure zero, which I use this notation for. And the morphisms in the category of measure spaces are the null set reflecting maps. So they're measurable, and that the pre-image of a measurable set is measurable. And the pre-image of a null set has to be null, which is this condition here, that if I have something in the codomain that has measure zero, its pre-image has measure zero. And that makes a category, which I call the category of measure spaces. And now you see why I called category of measurable spaces MBLE instead of its usual name, because I need a different name for measure spaces. And then I also need to, I need to do the thing I mentioned. I need to identify things almost everywhere. So I have to take a quotient of the morphisms. And the particular relation I use is not the usual almost everywhere one, but this one. But this one is really the right one. And I think this is in Tobias's paper as well as being, the correct definition. The other one is correct if you stick to standard Borel spaces, for instance. But in general, you need to use this one, where it does the same thing to sets in the codomain. So if you start with the same set, you don't necessarily get the same set. So the maps are not literally equal, but the difference between them is a null set. Okay. And then, so overall the idea is everything is up to sets of measure zero. So instead of the sigma algebra, we take the sigma algebra modulo null sets, which is at least a sigma complete Boolean algebra, although this will get rid of the points, for instance. And instead of working with the random variables, we do the random variables modulo null sets. And so that's what is represented with this Roman L infinity, in distinction with the calligraphic L, and that's why I used earlier this distinction between the calligraphic M and the bold one. The idea is to represent that when something is quotiented by null sets or not. So yeah, so I don't use all measure spaces, and it's not really possible, and it's also not a good idea. But unfortunately, I can't stick to probability spaces, and I can't stick to sigma finite spaces and these standard cases that we like to stick to. So I have to generalize outside them, and the way I go is to what are called localizable spaces. And there are several equivalent definitions of them, but they don't necessarily look the same at first. And then the definition I'm giving here really tells you why it's called localizable. There are other ones where other parts are more clear, but for this one, it's why it's localizable. So you have a measure space as before, and then there's a partition, not of measurable sets, but of measurable sets modulo null sets, and with each element being non-zero measure, but also finite measure. And by a partition, what I mean is that actually every join of the subset exists. So you only have a sigma algebra to begin with, so this adds an extra condition. You need to be able to make some infinite joins here in order for it to really be a partition. But this means that the Boolean algebra you have is not just sigma complete, but it's complete Boolean algebra. You actually then have all joins once you add this condition, and that it's a product of probability measures. So actually all I'm doing is I'm saying I have the probability spaces, and then I get rid of the null sets. Then I allow myself to take products of the algebras, which corresponds to taking kind of disjoint unions. But this partition it may not be literally a partition, because it's only almost it's only what do we call it? It's only almost disjoint. It's not properly disjoint. So anyway, and so sometimes you see this condition strictly localizable. That's the difference. And then we get rid of it. We don't want to deal with the non-localizable ones. They don't relate to probability theory. Okay. So how do we build up the monad? So could we just take the Giry monad and just put some more stuff on it? So no, I would have done that if it were possible. Can we go from, we can go from measure spaces to measurable spaces and forget the measure and then try and put something back? Can we do that? Well, no, we need to start with the quotiented out thing. So that's actually not well defined anymore because it took the quotient. So can we just do something with free and forgetful adjunctions? Is there some sort of free measurable space on a measure space we can use? And okay, well, yes, there is. But that's not a good way of doing it. And then the way I end up doing it, but it is sort of kind of more primitive. If you wanted to do it this way, you would end up having to do it the way I do it to begin with, to start off with. Okay, so there are two things. So that's a bunch of difficulties. How do we get out of these? So the first is we use duality, C-star algebras. And the second is, instead of starting with measurable spaces, we start with compact Hausdorff spaces, which have much better categorical properties, and they're a much better category. And then we will still have measurable spaces kind of in between these things, in between compact Hausdorff spaces, measurable spaces is in between, and then measure spaces. Okay. Right. So, but what do I mean by the duality I said earlier with C-star algebras? So I'll show it to you again in the case of stochastic kernels. So a stochastic kernel is that you have a function, so you start with a point, which is in X here. And then you have a measurable set, and then you put a number on. And then for every point, this is a measure. Okay. That's the sort of standard way. Then instead of considering sets, you can consider functions. With this is the bounded measurable functions, this L infinity. And so you just integrate against the value of the measure here. So you take the function and then integrate it. Or that's how you get up from a measure to something that's a state, which is something that's defined on functions. Then sort of the third way is you just swap the arguments. And then once you've swapped the arguments, what happens is you have something that's from measurable functions to measurable functions. But all you did to get that is to swap the arguments. And then what that is it's a linear positive unital map, what you get as a result there. And then the final way is to view it as a sort of measure that takes its values in functions instead. And then in the talk, I don't use it so much. I use it in the paper, and it motivates some of the terminology that I use, this point of view. And so this whole sort of point of view was, although it dates back to kind of the beginning of the subject, and sort of number 4 is sort of the standard way of doing conditional expectations. If you look in a measure theory textbook, the kind of categorical version of it, or the way it was imported into computer science, was by Dexter Cozen in these 2 papers. Then, without knowing about these papers, my supervisor, Bart Jacobs, and I did it for compact Hausdorff spaces, where we just use the middle 2. So we kind of ignore measures and just use states and positive unital maps. And then it means we can completely ignore countable additivity and things like that, and measurability. We just do use continuity. Okay, and the overall setup is that we have this thing, I've noted R here, which is the Radon monad. So that's the analog of the Giry monad in this case. And so this is the CleisLi adjunction for it. So you have compact Hausdorff spaces and the CleisLi of the Radon monad. And then you have an equivalence of CleisLi adjunctions, if you like. So this thing on the right, so this bottom thing is Gelfand duality. If you take the continuous functions on a compact Hausdorff space, you get commutative C-star algebras, the opposite category. And then the top one is the thing we defined in the paper, that is sort of the positive unital version, which is just this hurried swap of the arguments to get from a CleisLi map into a positive unital map. And if you work it out, so the left adjoint here, which is, it's actually, when you take away the ops, it's the right adjoint, but for the way it's written here, it's left adjoint, is just including a subcategory. So the bottom thing has essentially ring homomorphisms, although they also preserve the star, so they have this complex conjugate thing that you have to preserve as well. So that's called star homomorphisms. They're essentially ring homomorphisms preserving this complex conjugate. And the top thing has the positive unital maps. And then this is a non-full subcategory of that. And then the right adjoint is you take you essentially do the Radon monad in the opposite order. You take the continuous functions on the measures, which is the states here. Okay, so yeah, so that's what I said just now. Right, so that was the C-star algebras part. How do we get to W-star algebras? Well, so just as every commutative C-star algebra comes from a compact Hausdorff space up to isomorphism, every commutative W-star algebra is isomorphic to the bounded random variables modulo null sets, so complex valued, for a localizable measure space. And what a W-star algebra is just a C-star algebra that's the dual space of something. And the way that factors in here is that if you have a localizable measure space, then the bounded random variables, this L infinity is dual to L1, which is the integrable functions. And this is the thing that maps a density function to the measure it defines, basically. The category of W-star algebras is not a full subcategory. You have to restrict to something called normal maps, which are those that are continuous in the weak star topology, which is this unique topology defined by the predual. But you can also consider them to be Chu space maps, if you know about that, which is that maps that have going in the other direction on the preduals you have a map going the other way, a pre-adjoint. And then the usefulness of the abstract definition is that if you start with a C-star algebra, you can double dualize it and get the free W-star algebra. So because you put a multiplication on it, which makes it a C-star algebra, and then since it's a double dual, it's a dual space. Then this is the left adjoint to the forgetful functor. And apparently there is sort of no direct way or no perspicuous way of defining this in terms of this characterization at the top. So just because you know it comes from some kind of measure space. But then it took a lot of, for one of them I worked out explicitly, but it took a lot of work to actually work it out. The easier way to work it out is to just use the definition directly and use the universal property. Okay. So then there are several features that come together to let us extend the adjunction. So first is that, this way around now, that adjunction of taking the free W-star algebra is a monadic adjunction. And the second is that when you have a reflexive coequalizer of star homomorphisms, it's also a reflexive coequalizer in this bigger category of positive unital maps. And the third thing is that something that holds for every monadic adjunction, which is that everything in the Eilenberg-Moore category is a reflexive coequalizer of free Eilenberg-Moore algebras. So we can use this if we know how to do something in the free case, and it commutes with taking quotients, then we can go from something that's how we extend it basically. And so we end up with something like this. We have measure spaces down here and this equivalence, and then up at the top, and similar thing to what we had before, but it's for measure spaces now, not compact Hausdorff spaces. And so for the rest of the talk, we'll concentrate on the right-hand side because it's actually easier to define things first on the right-hand side. It's the opposite of what it was before. So before it was easier to define things in terms of spaces, but in this case, it's easier to define things in terms of algebras. Because we are in the opposite category, the situation for producing an independent product, the map goes the opposite direction. So we would normally take a measure on here and a measure on here, put them both together, but we have to go backwards. So it actually means we have an oplax functor instead, and we can get rid of the first H here, which was this comonad, but it's actually the left adjoint. So we can just get rid of it by, instead of working in this category, working in this category and using positive maps. So you have to find some way of combining two positive maps. And you might say, well, these are the coproduct and coproduct's a functor. Just use the coproduct. But this is not the coproduct of in the star category with star homomorphisms. It's the coproduct in this category, but we need it to be the coproduct in this category, which doesn't exist for the reasons mentioned earlier, that you don't determine a probability distribution by its marginals. So, and also, what are the coproducts anyway? Do we know them? And we need to know what the positive unital maps are out of them, not just the star homomorphisms. So to simplify, we go back to compact Hausdorff spaces again, but then we go straight from that to a measure, instead of taking the continuous functions first. And then this is a quotient. So this is a W-star algebra, and this is the free one. So this is actually a quotient, and this defines a surjective map. Actually, it's not just any old kind of quotient, it's a reflexive coequalizer. And we have that we know what the coproduct is for C-star algebras because of the duality. So this is something that doesn't work nicely for measure spaces because you don't have a perfect duality. But it does work nicely here. You have products must map to coproducts because it's a contravariant equivalence. And also colimits commute with colimits. So if I want to get this, I just take the quotient of this. So this is the coproduct, and this is the coproduct. And you also have the free, left adjoints preserve colimits. That's the other part of the argument. So it must be a quotient of that. So how do we characterize maps out of it? Well, they are positive unital maps that have what I've called truly continuous marginals. So the marginal map is that, so you start with something here, and then if you pre-compose it with this, you get the marginal map, so that total composition here, and this one here. And being truly continuous means that they come from something on bounded measurable, they come from measurable functions, so they extend to it, rather. Once you add that condition, so that condition is the definition, no, that's not the definition, rather. You define that, and that defines a functor, and then you can prove it's isomorphic to this. So that gives you your characterization. Then once you have it, you can actually prove what this is. So you can define a continuous family of mutually orthogonal states, and that proves that, so for each one of them, the thing you get is isomorphic to this, and then you have a continuum of them. So you take the power to the power of a continuum. So you have something that's not the coproduct of two things that are two probability spaces, becomes something that is not even sigma finite, that can't be expressed in countable terms. You need a countable number of factors to describe it. So then finally, how do you end up with the independent product map? So you can just use the co-unit, so the unit rather. The unit will get you from C of x will get you from L infinity of x into H of L infinity x. So you can use that here. And then you can use the co-projections, and then you just pair them up together. And then once you apply various isomorphisms to get it into the correct position again, you produce this map, which is what we wanted. And then it's still restricted to compact Hausdorff spaces, but luckily there's a way out of that as well, which is that we can apply Gelfand duality to W star algebras instead of C star algebras, using the fact that they are a subcategory. In fact, everything, it turns out to be expressible with compact Hausdorff spaces after all. So that argument turns out to be sufficient up to isomorphism. So that's the end. Thanks.
Thank you, Robert. The category of localizable measure spaces has another monoidal structure, if I remember, where we would get the null sets of the plane if we do R times R. That's not the monoidal structure that you're using, is that correct? Does that mean the Markov category has two monoidal structures, or does that not lift to the...
So I think the other one doesn't work. And they'll said also the other one, they're kind of only the same if you have a discrete measure space. Otherwise, they're different. But the other one is related to, is sort of still in there. It's still related to the independent products. So it's just that it's not the coproduct. That's the only thing. So it's the fact that I chose to use the coproduct is, but then the coproduct kind of gets you everything that's possible to be there in focus at once. Kind of what the truly continuous marginals thing is. Whereas with the different one, it's that you've kind of fixed that it has to be the independent product only. And I think that's why it doesn't work, or I didn't really check that case in detail, but I think it's not so good.
I wondered if it would be a product on the Markov, monoidal structure on the Markov category still, because it's quite an important monoidal structure.
Can I ask a question?
Yep, just go.
So have you checked also some possible axioms that this Markov category may satisfy, as in positivity, causality, conditionals?
So I think it does have conditionals, and that's kind of what I intended it to be, that everything has a conditional. But I didn't kind of get through to checking all these things. So that's something I will do in future work, is check that these conditions are satisfied.
Okay. Can I ask another thing?
Yeah.
I know there is a problem with the monoidal product when we move to the quantum world, but besides from the problem with the monoidal structure, do you feel we can get something like a Markov category, a quantum Markov category, if we drop the commutative? Okay.
Yeah, so that was also part of the motivation, was to drop commutativity and then do that case. But yeah, I haven't, that's future work, I think.
Okay. Thank you.
All right, let's thank the speaker again.